Hello and welcome to this video lecture series on microprocessor and microcontroller, and currently we are studying 8086 microprocessor. This is the 13th video lecture in the complete series and third video lecture especially for 8086. And in current video we are going to study the programming model of 8086, right? So in the previous videos, we have seen the architecture and pin diagram, and there were some clarifications from the previous video lectures that we will be making in this particular video before going to the programming model. And today we will also see how to write some simple programs in 8086 and what all is accessible as a programmer in this 8086 microprocessor. So that is the topic of today. So let me get you started by just opening my slides. Yeah. So we have already covered this architecture portion. So this architecture portion is known to us, and some important points about this architecture are that this bus interface unit and execution unit are independent of each other, and that is why the facility of pipelining is there in 8086. By pipelining, we mean that this fetch, decode, and execute, these three things are independent of each other, and the time wastage due to sequential execution of these three phases is not there as it was in 8085, but it is not there in this. So pipelining is available in 8086. It's a 16-bit microprocessor because the internal data buses are of 16-bit, and it can address 1 megabyte of external memory locations. So every memory location is of 1 byte, and that is why the complete memory is of 1 megabyte size. 1 mega is the number of locations and byte is the size of individual location. So these were some important points about this 8086 architecture, and you can see that most of the registers that you see here, they have some familiarity, they have some similarity with the earlier 8085 architecture, right? So the another important point is the flag registers that we have here are of 16 bits, and in 8085 a combination of your flag register and accumulator was called as program status word. However, in 8086 this flag register itself is called as program status word also, right? So accumulator cannot be combined with this to call this as program status word. So after that we saw this pin diagram where we said that it is a 40 pin IC, and in the last lecture we have seen the meaning of every pin in great details, and as we proceed in this course their usage will be clear to you. So in this context we have studied various tables, like we have seen this S4 S3 status bit table. So this S3 and S4, they are actually uh, you know, uh, with this A16 and A17 pins. So these are multiplexed pins. So the meaning of this is clear to us. That is, if S4 and S3 are 00, 01, 10, or 11, which segment is selected, it is indicated by these two status bits, S3 and S4. Then we talked about this BHE bar and A naught, right? So here we were discussing the memory structure of 8086, how external memory is organized into odd and even banks. So today I will first elaborate on this topic in some depth, and then we will move forward to the programming model. So we'll come back to this slide in a while. The next thing that we have studied on the last turn was the statuses of S0 bar, S1 bar, and S2 bar. That is, you can see these three here, S0 bar, S1 bar, and S2 bar, and this is for maximum mode. The things that you see in this bracket are for minimum mode, and the corresponding things that you see on this left hand side are in the maximum mode. So in maximum mode, the status is indicated by these S0 bar, S1 bar, and S2 bar, and you can see that these are the interpretation according to whatever is the value, I mean whatever is set or reset on these three pins. So this was one thing that we saw on the last term. And then we also saw that there is an internal queue, instruction queue of 6 bytes in 8086 microprocessor. So to be able to check what is happening on the queue, we had these. two bits, QS0 and QS1, right? In this QS0 and QS1 are pin number 24 and 25. And what do they tell you? They tell you what is currently happening with the instruction queue, right? So this is no operation. If it is 0, 1, then first byte has been accessed. And if it is 1, 0, the queue has been emptied, maybe because of a jump instruction or something else that diverts the control from one location to another. So you have to discard the code that is written after that and you have to jump to that location. So that is what we mean by empty queue, right? And then 1, 1 is subsequent to byte has been fetched. A byte which is other than first byte has been fetched from this uh, instruction queue in the last instruction, right? So this was what we have studied, and this is a more clear diagram of this pin diagram of 8086. It is more clear because it also shows you the directions of the signals that you can have here. So it's essentially the same diagram that we have seen on the previous slide. It is the same, but it has an additional information in terms of the data that can be transferred in which direction onto these pins. So this is a more clear diagram. So here you can see that uh, this address bus it starts from A0 and it ends at this A19 here. So from this AD0 it covers these all pins and these all pins are there. So it completes itself at AD19. So there are a total of 20 address pins. That's why it can access 2 raised to the power of 20 memory locations of externally interfaced memory, and that's why it's called that's why uh, we have 1 mega locations there. And also this address bus is multiplexed with data, and since data bus is of 16 bits, so you can see that from D0 to D14 and this D15 you have got a total of 16 bits, which actually are multiplexed for data bus. I mean, you have one complete address bus from AD0 to AD19, and on the first 16 pins, that is from AD0 to AD15, you have got multiplexed data bus. And to be able to segregate the addresses and data, we definitely have a address latch enable signal here, which can be used for our purposes. So this is the kind of direction of the data flow. You can see that up to the point wherever your data bus is multiplexed with the address bus, these are bidirectional pins because data can be taken from the microprocessor and can be sent to the outside world also. However, remaining pins of this are unidirectional only, right? Similarly, you can look at other signals also, and you can justify it for yourself that why is the direction outwards or inwards, right? So this is a more clear diagram of what we saw on the last turn. Now this programming model. So this is the programming model of 8086. A similar kind of model we have seen for 8085. And as you can see here, whatever is accessible to programmer has been pasted on this particular slide. So you can see we begin with these general purpose registers. So you have these general purpose registers, which you can see if you use them combinedly. AH and AL combinedly are called as AX, BH and BL are combinedly called as BX, simply, and similarly this is CX and DX. So you can say that you have four general purpose registers of 16-bit each, right? Or alternatively, you can say that if you see them as 8-bit registers, you have got A higher, A lower, B higher, B lower, and so on and so forth. So you have got 8 general purpose um, registers of 8-bit each or 1 byte each. So you can say that you have got one word registers which are 4 in number. One word means 2 byte. So you have got 4 one word registers, or alternatively you have got 8 1 byte registers, or alternatively you may use any combination between them. You can use this BX register as a whole as 16-bit and maybe CL register as only 8-bit register. So any combination can be used. So we have got these general purpose registers here. General purpose means they can be used for any purpose. However, later on we will see that this CX register is usually used for counter operations. When we will study loops in 8086, we will see that this CX is usually used for counter operations, and every register has a specific purpose. Another important point to note here is that the accumulator now here is little bit free of responsibilities as it was in 8085, because in 8085 whatever calculation happens inside the microprocessor, the result of that will be by default stored in the accumulator, but here it will not happen. Here the result will be stored in the register in which we will specify, right? So in that way, this accumulator is little bit free as compared to 8085, but it is still called as accumulator because for some default calculations, it is still used as the default register, right? But not for all of the calculations as it was the case in 8085 microprocessor. Now, after general purpose registers, we have got these index registers. Index registers means the full form of this is source index and this is destination index, SI and DI. So these registers are used in combination with various segment registers that you see here, right? So let me first discuss the segment registers and then we will discuss these index registers, pointer registers, and control registers. So segment registers, these are again 16-bit registers, right? And what are they used for? In 8086 microprocessor, the externally interfaced memory is of 1 megabyte, and we said that inside that 1 megabyte memory, you are free to create your code segment, your data segment, your stack segment, and your extra segment. So since the memory is of 1 megabyte, we have got 20 bits, 20 bit of address for every location. 20 bits, or in hexadecimal we can say that 5 hexadecimal digits address will be there for every external memory location. But there is a boundation on the starting address of code segment, data segment, stack segment, and extra segment. If you see the hexadecimal representation, the address will be of 5 hexadecimal digits for the externally interfaced memory, and the boundation for um, starting address of code segment, data segment, stack segment, and extra segment in the external memory is that the last hexadecimal digit has to be 0, or the least significant hexadecimal digit has to be 0 for that case, right? So that way we are only left with 16 bits. And inside the microprocessor, to hold the starting address of that, we have got these 16-bit segment registers: code segment, data segment, stack segment, and extra segment. So this is not the code segment. This is a register which keeps the first 16 bits address out of the 20 bits of code segment, right? Because the least significant 4 bits are by default 0. This is a restriction in 8086 that wherever you start your segment from, it has to begin in that way. So these segment registers are used for that particular purpose. So these are 16-bit registers, so they consume 4 hexadecimal digits, and if you want to take the starting address of any segment, you have to append a extra hexadecimal digit, which is 0, after these segment registers. Now, in combination with this segment registers, we use index registers. For example, we are working in data segment. So suppose the actual physical address of the data segment is 50,000 in hexadecimal, right? 50,000 in hexadecimal. So last hexadecimal digit has to be 0, which it is in 50,000. The last digit is already 0. So this data segment will keep 5,000 in itself, 5,000 in hexadecimal in itself. Data segment register, which is internal to microprocessor. The remaining 0 is implicit. So this data segment will contain that particular address. Now, inside that data segment, you have got 64 kilobyte of memory in the externally interfaced memory, uh, starting from location 50,000, and after that you consume 64 kilobyte locations. So that complete section will be called as your data segment. In that data segment, if you want to navigate, you have got this source index and destination index register, right? So this source index and destination index register is nothing but after this initial 50,000, where we are going inside the data segment, it can be kept here. Suppose I want to access a location of 50,004, 50004. So data segment will contain 5,000 because it's a 16-bit register, and a 0 is implicit after that in hexadecimal because it is a constraint, and this source index may contain 0004. 0004, because every segment is of 64 kilobyte. So to be able to address every location inside the 64 kilobyte, you only need 16-bit addresses. So that is why this segment index, it contains the offset. It contains actually the uh, index of locations within that 64 kilobyte segment. So this SI will contain 0004, DS will contain 5000. So if we want to calculate the actual address from DS and SI, what we will do is we will take 5000, append a 0 after that, so that it will become 50,000 in hexadecimal, and then SI register already contains 0004, so we will add it to that. So it will become 50,004. So that is the way we calculate these addresses. So we have got the actual physical address, then we have got base address, which is kept in this DS register, which is the beginning of any segment. And then inside that we have got this logical address. SI contains the logical address. Now, implementing addresses in this way is important because if you somehow try to change the starting of data segment in your program, right? So you can simply just change the content of this DS register. Rest program will remain same because SI works on relative address. The value that you will keep in SI will be relative to DS. So even if you change the value of DS in your program, this SI does not needs to be changed because SI is already relative to DS. So we will see this when we will see an example of coding. So there it will become more clear to all of us. Then similarly for DS, you have got this SI and DI pairs. This SI and DI pairs can also be used with your extra segment, right? For stack segment, we have got stack pointer. So this is called as pointer registers. For stack segment, we have got this pointer register, right? For code segment, we have got instruction pointer. So with code segment, instruction pointer will be used. With data segment, SI and DI can be used. With stack segment, stack pointer can be used. And with extra segment, you will be able to use this SI and DI again, right? So we have got index registers. These things, they contain the logical address. That means the address after the base address of the starting of the segment. Then we have got pointer registers. So stack pointer is used for stack operations. Base pointer, as you will see, it will be used for implementation of a double pointer in 8086. So I will elaborate more about this base pointer when we will study the addressing modes and programming exercises. So we will see more about base pointer there, right? Instruction pointer, which is a control register, it is used for code segment. Why is it called as control register? Because CS and IP, the combination of CS and IP will contain the address of next instruction to be executed, right? So I told you in the beginning that instruction pointer is similar to program counter in 8085, but not instruction pointer alone, a combination of code segment register plus instruction pointer, because CS, when we will apply a 0 after that and then we will add the value of IP in that, we will get the actual physical address of the next instruction to be executed, right? IP only contains the address of the next instruction to be executed relative to code segment. So CS and IP combinedly, they will give you the address of next instruction to be executed, right? So we are already aware of this flag register. You can see that this is the format for flag register. So we have got carry, parity, auxiliary carry, zero flag and sign flag. So up till now, these 8 bits are similar to the flags that we have used in 8085. Then you have got trap, then you have got interrupt, then you have got direction flag, and then you have got overflow flag. So these are the extra flags that have been there. So you can call this as a flag register, or you can call this as program status word, right? So in 8085, program status word was a combination of accumulator as well as your flag registers. Here it is not the case. Here the flag register itself is called as the program status word, or PSW. And PSW is accessible to user by this command called as PSW. So we will see it when we will study the instruction set of 8086 in complete details. So these are the details of this programming model that is available to the user for programming this 8086. So now in this lecture, let us begin with some very simple codes to be able to understand which software we will be using and how programming is done in that. So let me just open the software that I have got, and you can also download that software. Its trial version is available for free usage, but I think that is limited for 14 days. So for learning the programming of this with a better visualization, this software is very good. And after we are comfortable with programming in 14 days, we might switch on to some open source alternatives, which will not have that good visibility. But still, since we understand, we will be able to make our programs. So I'm running this software in trial mode only. So this the name of this software is EMU 8086. So this EMU 8086 will be available on the internet for free for download. You can download and install it. The installation is fairly simple. It's just double click installation. So this is how the interface of that looks like. And let me just open a code that I have written already for you. You can write the code here, but let me just open one set of code here so that we can understand how coding is done here. So I have already written this program. So the programming remains mostly similar to what we had done in 8085. Here you can see that whatever you will write after semicolon will be treated as a comment line, right? So I have written a lot of comments in these initial programs so that you will be able to understand things better. And what this program achieves is, this is a program to add two numbers using the internal registers of 8086, right? So through this program, we will be able to understand a couple of differences between 8085 and 8086. As I told you, that accumulator here is little bit free. So in this program, we will see that by default, the calculations result will not be stored in accumulator. It will be stored in the registers in which we will specify it, right? So what we are going to do is, from the programming model, we are taking only 8-bit data here. We are taking 8-bit data and we are keeping it in AL register and BH register. So you can simply see that in AL and BH, you have kept this data of 02 and 05, and then we are adding the contents of BH and AL register, right? And the default result will be stored in BH register, right? The result will be stored in BH register. So let us understand this code line by line. So MOV AL, 02H. So if you see 8085, this command would be invalid there, because for moving the immediate data, you will be using the command MVI. But in 8086, we do not have that command MVI. All we have is move. So move is used for moving immediate data to any register, or the data from one register to another register. So here MVI command is not there. All we have is move, right? So this AL command, this AL register is there, and in that we will be moving a 8-bit data or a 1 byte data or two hexadecimal digits. So 02H has been moved into this. Similarly, 05H has been moved to BH. And when you add them, now you can see that there are two arguments. Earlier in 8085, one register was accumulator, which was by default there. And whatever you want to add it, it was written after that. So only add will only have one argument after that, but here both arguments are there. So in 8086, the format of writing these arguments is destination comma source. So destination comma source means whatever will be the result of this command. Add command will definitely add something, subtract command will subtract something. So whatever will be the result, it will be stored onto the destination, which happens to be BH in this particular case, right? So the format is destination comma source. If I would have written AL comma BH, then the result will be stored in AL after calculation. So this is something that we need to understand in this 8086. Accumulator by default will not store the result of all calculations. For some calculations, yes, it will store the result, and I will let you know what those commands are. But for most of the calculations, you have to specify the destination by yourself. And that's such a big relief, because if accumulator is kept busy all of the times, then it makes things difficult. So in 8086, this provision has been added, and this provision has been carried forward in all the Pentium processors and i3, i5 series, etc., and so on and so forth. And then HLT is a similar instruction which we saw in 8085. Now, to be able to run this program, you need to press the emulate button, right? So when you will emulate it, you will see these two windows will open. Now, the good thing about this software is that it will, on the second window, it will mark the next instruction to be executed in yellow, right? And corresponding to that instruction, this memory is shown here, right? This memory is shown here. And you can see that inside this memory, two portions have been highlighted. So it automatically tells you that move AL, comma 0 to H is a 2 byte instruction. It is consuming 2 bytes in the memory, and it is also giving you the equivalent of that. Move AL equivalent is B0, and 02 is already in hexadecimal, so its equivalent is 02, right? So this is the good thing, that whenever you try to emulate this program, in that case, the next instruction to be executed will be highlighted in yellow, and whatever amount it consumes in memory, it will be highlighted in blue. On this side, you can see that you have got this instruction which is already written corresponding to that. So this is essentially the same thing that you have seen here, but it is also highlighted here. Another important point to see in this particular interface is that you have got the hexadecimal equivalents as well as their decimal equivalents here. So whatever notation you are familiar with can be seen. And also, if you expand this a little bit, you can see the ASCII representation of that also, right? So this is not of our use, ASCII representation. So we will stick to this hexadecimal and decimal only, right? So this is the thing here. Then after that, you can see that you have got all the registers: AX, BX, CX, DX, then CSIP. They are shown together because frequently you will be accessing them together. Then there is a stack segment register and stack pointer register. So they are shown together. Then you have got base pointer. We will see what this base pointer is. And then source index, destination index registers are there. Then data segment and extra segment is also there, right? So this is the programming model, complete programming model. The things which are accessible to the user are obviously shown here, right? And if you want to see the status of flag registers, you can go to view. And I think there is something for flag here also: memory variables, listing options. Yeah, flags. So you can see the status of flag registers also. Don't cares have not been listed here, but all the bits of the flag have been shown here. The useful bits of the flag have been shown here too. And rest things we will discuss later, that how memory is shown. Even if you want to see the memory, then view and memory. So this way you will be able to see the memory. And suppose if you want to see inside memory, the suppose the data segment begins from 50,000. So you will definitely put 5,000 here, and you want to see 50,000 fourth location. So you will put 0004 here. And when you will press enter, you will be able to see that particular location here, right? So this is how you see memory, and in the same way you can browse this complete memory also by just putting the base address and the offset address here, so you can reach to that particular location. Now another important point is you can already see that since the code is already written and we are already trying to execute it, so what is happening here is that code segment must have been initialized, but we haven't initialized it as yet. So some default value is taken. So that default value is CS0100 and IP0000. This value has been chosen by this emulator. It's not a fixed value, but for this emulator, this is the fixed value. It has started its code segment from 0100 and an additional 0, if you want to talk about the actual physical hardware address, right? So this is the beginning of the code segment. Interestingly, you will also note that data segment and extra segment, they also begin from 0100 and 0100, right? So it is actually overlapping all the three segments, that is code segment, data segment, and extra segment to begin with. Some machines allow that. Some machines allow your segments to be overlapped. Some machines, they do not allow segments to be overlapped. So it depends upon which vendor you are using. But theoretically, all these four segments, if they are defined in memory, they should be kept separate. So some vendors allow overlapping of these segments and some vendors do not. This program software, it allows you to do so. If you want to set their values, we will see the code for that also, how you can initialize your data segment, code segment, etc. in the very next lecture. So we are going to see that. Stack segment, you can see that it is also initialized from 0100. I mean, all the four segments are initialized from the same location. And the instruction pointer, source index and destination index, they have been initialized with 0000. However, stack pointer is initialized from FFFE. So stack, it already begins from the downward side of the memory and it populates upwards. So that is why this stack pointer has been initialized from FFFE. So SS in combination with SP will be used for accessing the stack, right? So this is the interface, and if you want to run this program step by step, let me run the very first command by pressing this single step button. So you can see that 02 must have been moved into AL register. So 02 has been moved into the lower byte of this AX register, which is called as AL register, right? Similarly, let me execute the single step again. So 05 in BH, 05 in BH. Now this is important command. On the addition of BH and AL, you will get 2 plus 5 7, and that 7 will be stored in BH register. So this is an important point to note because it is different from 8085. So let me run this. So you can see that the content of BH register, the higher order byte of that, has become 7, and accumulator is unaffected by that. So this is a great achievement, I would call, that we have got in 8086, because accumulator is now free, right? So then again the halt instruction is there. So it is just the emulator is halted. So in this way, you can run your programs on this emulator. And from the next lecture, we are going to see some very basics of how to deal with stack, how to see the memory, and how to initialize our own data segment, stack segment, etc. And what all things are there. So that's what we are going to see in the next lecture. And mind you that this software is a trial version, so you will be able to run it for free for maybe 14 days. And after that, it will stop working on your computer. Then you have to reformat your computer or Windows and then reinstall it again. So in 14 days, we should get a very good understanding of this coding of 8086, and then we will use an open source alternative, because that's the time that this software allows us to use, right? So I guess this is it for this particular video lecture. I'll see you in the next video. Thank you very much.